Hello, ladies and gentlemen, those who are watching now or those who will be watching later. Welcome to our next lecture on the topic of Bayesian data analytics for automatic and robotics studies at AGH University of Science and Technology, or now it's called University of Krakow. And welcome to our next lecture, today's lecture, which will cover generally how to compute the expectations of certain functions, which really translates to computing any kind of quantities of interests, which in a way results to us to Monte Carlo computation. That's why the title of the movie, of the video at YouTube is called Introduction to Monte Carlo Computation. Hopefully we'll be able to handle most of the topics. I intend this stream to be around 1 hour or 60 minutes. So, without further ado, the main point of probabilistic computation in general is computation of expectation of certain functions of parameters. So we assume that there is a joint probability distribution that describes the parameter and data, and we want to have some kind of information that represents the joint distribution, in particular some kind of quantity of interest. Sometimes we are interested in the expected value of certain parameter that, for example, is the effectiveness of certain medicine, or sometimes we want to determine causal effects between one and another. Sometimes we want to determine strength of relationships, and sometimes we are interested in some kind of utility function, for example, the profit that comes from the use of certain models. So we can represent what kind of gains and what kind of losses we can get from the observation. So, however, what is important, computing an expectation is not the same as computing the mean. It is computationally related because we will be generally using averaging of samples in order to compute certain expectations. However, any kind of statistic can be represented as an expectation of certain function. And because of that, it is much easier to compute a lot of things thanks to reformulating the problem into the problem of computing an expectation. So let us consider and start some situation more abstractly. We have some kind of a function of a vector of parameters describing our models. Because we assume that we have a model that is parameterized by a finite number of parameters, so this is a vector, and we have a function that's in some kind of way represents a quantity of interest related to that vector, and more precisely to the probability distribution of that vector. It can be a very simple function, like for example a point evaluation of one of the parameters. It can be a complicated function, for example a solution, certain function of a solution of differential equation which uses the vector of parameters as parameters of this equation and its initial condition. We solve the equation. So the function can be complicated in multiple ways. Usually we want this function to be relatively normal, so it's called we want it to be measurable, so it won't create some kind of weird situations. But generally we want to compute what will be expected value of what is the expected value of that function with respect to a certain probability distribution in the case of continuous variables, or probability mass function in case of discrete variables. So in order to compute what is the expected value of that function, we compute certain integral over the entire parameter space Q, large Q, of the product of our function and the probability density function of the regarding parameter Q, or in its case, again, in the discrete case, we do not integrate, we sum over all the possible values of Q. The second case is much easier, but unfortunately many cases are not as that easily translatable to the problem of computation. So how can we get that expectation? Because as we've seen on the previous slide, it is rather complicated integral or complicated sum, because we already know that posterior distribution or joint distribution of parameter and data are rather complicated objects. Analytical computation of that expectation is not really possible. So we need to find some kind of reasonable way to compute such expectation. And for one of the main ideas that is popularized in classical statistics are model estimators. And model estimators generally says we compute the maximum of the posterior distribution. So we find the point that is the highest in this function. Then, if the function, we can observe that if the function is reasonably well behaved, the value of the expectation is close to that maximum. There are certain important requirements for that function, but in practice this is something that we that happens in more simple cases. So we treat the posterior function as a function to be optimized. We use numerical optimization and we find that maximum. And as long as distribution is relatively well behaved, it is all okay, because these actual mean or expectation of the function will be relatively close to the mode, the maximum of the distribution. However, if function is much more skewed, then we can have a larger problem. If a mode can be easily away from the mean, the most obvious case that we know is the distribution of the salaries in Poland, where we have this value which is a national average salary, which is relatively high, and we have the mode value, the maximum, the number of how much people are earning in the biggest number of people are earning what kind of number, and that one is very close to the minimal possible salary. However, because the distribution is highly skewed and has a heavy tail, so there are billionaires that are being computed in that average, then there is this large discrepancy between the mode and the actual expected value. So skewed distributions can cause the maximum to be far away from the expectation. Moreover, there are problems if function is multimodal, because if multimodal functions finding a global maximum is a problem. The more parameters you have, the larger the problem is. And finally, there's problem with quantizing the uncertainty. We can find the value expectation, but we are completely unaware how well it represents our data. And at least this is something that we think that what is the uncertainty of that actual value. The idea to improve that is to create some kind of approximation that will include both the mode estimation and also the some kind of uncertainty quantization. And this is a very old idea, but still very effective, called Laplace approximation. Laplace approximation was, of course, proposed by Pierre-Simon de Laplace, and its general idea is that to create the approximation of the probability density function or probability mass function in the parameter space around the mode of the distribution, assuming that if we capture the shape of the distribution by this approximation, we are relatively well prepared to quantify its uncertainty. And the idea is, of course, to use Taylor expansion. However, not to use Taylor expansion directly on the distribution, which is obviously not a polynomial function, because it's a function that integrates to 1 over the entire probability space. So this is not something that can be expressed as a polynomial. However, the logarithm of that function is much better to approximate using the simple Taylor series expansion around the maximum. Moreover, because it's a maximum, this approximation is even simpler because this first term, the term corresponding to the first derivative, is obviously 0 because this comes from the optimality conditions. So what we're really interested in is a Hessian matrix, which is the matrix of second derivatives of this function around it. And this gives us a quadratic, at least in the form of quadratic form, representation of logarithm of our function close to the maximum. The further away from maximum we are, the larger will be the errors of this sum that we are not listed here. And to come back from the logarithm, we can then use the we can just take an exponent of both sides. So we remove the logarithm on the left, and we take an exponent of this quadratic function, which is obviously a Gaussian probability distribution, that is Gaussian shape. So this is a proportional to the normal probability distribution conditioned on with a mean of in the mode and the covariance matrix represented as the inverse of the Hessian matrix. And the expectations are given by Gaussian integrals, which are easier to compute because they will be the function multiplied by the Gaussian, and this is something that we can handle. However, Laplace approximation still has limitations. All the distributions that are being created with this approximation will result in some kind of normal-like distribution. So its level set will be a level set of some kind of ellipsoids around the mode. And depending on how our function is related, similar to the ellipsoid, the approximation will be better or worse. So this is a strong limitation, which does not necessarily mean that Laplace approximation is not usable. Laplace approximation is usable in multiple problems that are relatively close to normal distributions. For example, normal distributions with normal priors for parameters and certain changes in the parameter, changes in priors for example, standard deviations or other variances. So it can work, and also it rather well works for approximation of not the entire distributions, but some kind of marginal distributions where such things work very well, and is a base of so-called INLA computational package, which is INLA, which is a computation package allowing solving certain Bayesian problems using appropriate approximations. So if the Laplace approximation is not enough, and in complicated cases, more complicated than trivial, probably will not be, we need to look for some other options. So perhaps compute the expectation integrals numerically, which is using the quadratures of those functions. And this is something that has certain limitations. If we have only one variable, the quadratures in 1D are very, very simple. They can be solved by if we have a bounded interval where we compute the expectation, they are trivial to solve using interpolation quadratures or Gaussian quadratures or adaptational quadratures. In case of unbounded intervals, we need to use some kind of variable changes to transform it, or use some kind of dedicated unbounded interval integration methods like Gauss-Hermite or all real numbers, or Gauss-Legendre for positive real numbers. Those things are useful for computation of such integrals. However, computation of integrals in higher dimensions is a much, much bigger problem. And it all depends on the geometry. Because generally, in order to integrate certain function, we need to compute its values in the given set of parameters, and then using those values compute the quadrature. The problem is that the higher dimensional dimension is, the less and less space points where something of matter occurs in the function. Most of points will be very, very close to zero, and it comes from the fact that the function has to integrate to 1 among the others. But also because of the function, the space is rising much faster than the function values. If the shape of the distribution is highly skewed or modified, the values that we compute, for example here and here, have so small values that they do not contribute to the computation, and on the same side are introducing biases in computation or introduce additional computational cost. And in order to understand that, we need to understand what the integral really is. Because expectation integral is the integral of product of two functions, and additionally the growth of the variable d cubed. So our one-dimensional intuition, because most of our integration experience comes from one-dimensional case, because this is easy to plot, so that's when we can understand that. The intuition says that wherever the density function, or this product of density function and function of interest is large, these are the points that contribute to the integral the most. The higher the function is, those values are more important. So the closest we are to the maximum, the biggest values we are. So that is our intuition in the one-dimensional case. However, this generally looks like this. Our density function, when considering the distance of point Q from the mode, at zero distance has its maximal value, and the further away from the mode, the smaller the function is. However, this situation completely neglects the aspect of the volume. if we have an interval and we divide this into the three parts and we have a Gaussian over it, we can relatively reasonably assume that this part will be contributing the most. But we need to understand that if we focus only on computation here, we drop 2/3 of the volume of the function. In two-dimensional situation, it is even more interesting, because if we focus again at the relative closeness to the mode, so the biggest values of the function, our unimportant points in the parameter space now take 8/9 part of the space, and only 1/9 part of space is here. In three-dimensional case, we have and in further we have generally a geometric progression. We have 1/3 over. We have in this case 27 possible cubes around this, and 26 of them are empty or not considered for our analysis, and only one in the middle is. So we are losing 26/27 of the space. But at the same time, we do not want to sample all the values in this space, because we want to reduce our computational cost. So the further we are from the mode, the larger is the volume, because when the shape expands, the more and the more points of volumes are happening here. So the further we are from the mode, the more and more function is contributing, the volume is contributing. And our integral is the product of distribution times the volume points. So that gives us that the actual expectation contribution doesn't come from the points next to the mode, and of course doesn't come to the points far away from the mode, but they come from the points that are somewhere in between. Points that are away enough from the mode to contribute, but not away so much that their contribution is negligible. And generally, we call the area of where the most contribution to the expectation from considered probability distribution and its parameter space, called typical set. This typical set is the area where the product of function with respect to maximum and its and the rising volume is the largest and is contributing the most. This is called a concentration of measure, because this typical set is not well defined with some kind of a fuzzy surface that is not precisely defined, which is progressively away from the mode the bigger dimension is, because then the volume rises faster, so it moves farther away. And we can see that we're increasing the dimension, which can be shown mathematically. We won't be doing that, but you will have to believe me, that increasing this dimension will further and further contribute most of the probability in the typical set. And an example of typical set is some kind of like a fuzzy surface without well-defined borders, just some kind of fuzzy representation. And we are interested in that because samples from the typical set of the distribution can quantify this distribution behavior. Just knowing samples from there, we can easily estimate the quantity of interest. But what kind of thing is sampling from the typical set, or generally sampling from the distributions? And why we are interested in that? Well, we are interested in that because we kind of don't have another option. We want to compute the expectations. We cannot compute them reliably using integration, and we are not sure about the representation faithfulness when using Laplace approximation, so we kind of need to get something more. And sampling helps us because as long as we can generate samples from the distributions such that the average of values of function of interest in those points converges asymptotically to the actual expectation, then our sampling procedure is what we call exact. Exact sampling procedure that generates the values Q1 to Qn from the parameter space corresponding to the probability distribution pi. And as long as we generate those quantities, we can say that the estimate of the expected value, Monte Carlo estimator of function f using n samples, has a normal distribution that corresponds to, has a mean of actual expectation as the standard deviation of so-called Monte Carlo standard error. And Monte Carlo standard error is defined as the variance, the radical of quotient of variance of our function f corresponding to our distribution divided by number of samples. This is a very good situation because generally the average of samples generated from one distribution that are independent from one another follow the central limit theorem. So the error of our Monte Carlo estimator is normally distributed. The values from that estimator come through the using the given measurements are normally distributed, and as long as n is large, we can consider it normal. If n is small, the distribution has certain higher order terms that cannot be neglected. Monte Carlo standard error, as I said, is a radical of quotient of variance of f divided by n. And using the Monte Carlo standard error, we can measure the absolute error, how much to the absolute value we are away from our estimate. So we have some kind of absolute value uncertainty. And this can be estimated directly from samples using the appropriate values of samples and necessary radicals. However, for small values of expectation, we are sometimes much more interested in the relative error, which is reasonable, because if our actual value is in microns, so we are much more interested in the percentage representation from that, and that is, of course, the quotient of Monte Carlo standard error by the estimate of the expected values f. This can be very useful in situations that we want to ensure the relative precision, because in order to get the number of samples, well, we need to say, in order to get some kind of good representation of n, we need to get n to minus 3 over 2 small. In case of getting relative errors, if we want to have a relative precision, let's say few percent, we need to use this following formula, which uses both estimated variance and estimated mean and the parameter of precision of alpha. So that will get us the required number of samples. And this idea of computing expectations of using averages for functions of interest opens us the possibility of multiple kind of summary function sample summaries that we can use as a Monte Carlo estimator of what we want. So we can use moments and cumulants, so we get means, standard deviations, etc. We can consider even probabilities. In discrete case, it's easier. In the continuous case, it's a bit more difficult because we need to consider the integral over parameter space in order to define the event. We can use histograms, we can use empirical cumulative distributed function, we can use quantiles, we have a lot of options. Moment and cumulants are probably the most popular, which most people know only about moments because this is mean and variance, and some people also know kurtosis and skewness. Cumulants are much less known. They are generally moments but slightly rescaled. They are very useful for summarizing certain things because we can capture some more information. However, this is not the limitation of what we can use using expectations, because what we very often want is to get a probability if the quantity of interest is located in certain interval. And this is being done by computing an expectation of the so-called indicator function. An indicator function is one of the simplest functions. For given interval or set, function is has a value of 1 if for given point, if that point is in that set, and 0 outside of that set. So, computing of expectation of such indicator is relatively trivial because the integral reduces to a sum, because function takes values of either 0 or 1 depending on the given value. So, in order to estimate the expectation of such indicator, we just need to compute its arithmetical average of the function values and then in the indicator function. So we generally need to compute the number of times how many considered values are located in the set of interest, and then divide it by the whole number of samples. So we will get easily the probability estimate as such quotient. Probability estimates are not equal to, for example, moments and cumulants, because moments and cumulants are relatively easy to compute their own uncertainty. The Monte Carlo standard error is kind of well defined because of the variance and stuff. In case of indicator function, it is also simple, but with certain caveats, because using that we can actually get an absolute error given by the radical of p, so the probability of point B located in a certain interval, times 1 minus p divided by all the number of samples. And if we consider a relative probability, we need to divide that by the appropriate number, and for, in this case p squared. So, and that will give us the p, which will be p squared under radical, which there is some kind of cancellations, and we get a radical of 1 minus p over n times p. And this actually gives us certain information, because it says us that, for example, if we want to have a relative error of 5% regarding to a certain number, we need to provide appropriate recomputation. If we want to ensure that the relative error will be 5% or less, then we need to perform such computation, and we will get in the number of 39,000 samples, which is generally reasonable. Because if you look at it from the outside, the probability p of 1% is relatively rare. So in order to be certain about how probable that rare event is, then you need to observe at least some of those of its instances, and the probability and if the event is rare, then you need to observe a lot of events in order to observe instances of that one single event. Other useful statistic that is being used to analyze the quantities of interest is the histogram. And here we will discuss a bit of histogram that's not typically discussed. That is the situation of uncertainty of the histogram, as a histogram is in a certain way of representing the probability density function of estimating the entire probability density function. And depending on the approach we will use, we can consider it either as a probability mass function of separate events, or just the estimate of probability density function. Either way, that enforces us different kinds of normalization in order to get the histogram, which is again simple function of just how many points are given for given a sample are located in certain intervals. And depending on what kind of understanding, we can either not normalize those values and just use counts. We can use counts divided by number of samples, and we will get this representation as a probability mass function, or we can just find a way to represent the functions in a way that will be consistent with integral of function equal to 1. A sister to histogram is empirical cumulative distribution function. The histogram is a function that allows you to observe the estimate of the entire probability distribution function. ECDF is a function that wants to approximate the cumulative distribution function using just samples. And while histogram is a very local function that allows you to represent certain local behavior, the ECDF is more global, showing the entire cumulative distribution function. And this is a very funny function that is much easier to define as a code than as the actual formula. And the code is very simple. Just you take a vector of samples, you sort them, and then you assign the probability values of those points as starting from the smallest one up to the highest one, as long as they are not duplicating. This is very simple, because just the function adds an additional quant of the 1 over the number of samples to the actual function of cumulative distribution function. And because it is actually a collection of all possible interval estimates from the lower end of the interval up to the highest end of the interval, so the probability of something belonging to the entire probability space, its uncertainty is analogous to the estimates of probability estimates. Finally, very important aspects are quantiles, which is the inversion of the probability of a given interval. A p quantile is the point where the probability of interval from minimal value of y up to this point is equal to given p. So quantiles are defined by probabilities. Preferably those are easy to remember percentage probabilities like 5, 95, or 25, 75. Those numbers are simple to represent. And of course, they are not unique. You can use any kind of value p between 0 and 1, representing the percentage. And depending on and this can be of course computed in the same way as just by counting the samples in a given interval, in a certain situations modified by adding the interpolation. And we know now what kind of statistics we want to compute. We said Laplace approximation, easy, Laplace integrals, often imprecise. Numerical integration, not doable because of the ever-increasing space of the probabilities. So random sampling is an option because it's quantified by Monte Carlo standard errors. It's relatively easy to understand. These are just averages. It's okay. But we have one single but, which is actually a big but, and not in the good but kind of way. Generally, we need to find a way of obtaining random samples, and moreover, those random samples should be coming from the probability distribution of interest. And we have relatively two options to get random numbers in our computation. One is hardware random number generators. This is something that pops up once every other time in scientific world as a solution to many problems that were invited by the developer of that problem, of that solution. Generally, hardware random number generators work like this. You take an electron lamp, like in those audio amplifiers, and you use that electron lamp, which generates naturally a lot of noise. You measure that noise, you provide some kind of band limitation usually, and you use that to represent the values, the random values coming from the universe. There are applications from pseudo-random, some hardware number generators. As again said, some people are very fond of them in cryptography, but most of computation is being done using pseudo-random number generators. And the pseudo-random number generator is a mathematical formula. Mathematical formula that allows you to generate a sequence of numbers, one after another, in such way that this sequence of numbers has low autocorrelation, so there is no natural relationship between one another, has a possibly long period, so it's not something that will be repeating itself anytime soon, so we're not able to predict the values, and has uniformly distributions of quantiles of numbers. Those are the main requirements. And the simplest way of finding such number is to generate the integers in certain intervals, usually between 0 and m. And it's being done by computing those integers, multiplying them by a constant, adding additional constants, and computing the modulo operation, which will always constrict our solution to the values between 0 and m. And appropriate choice of parameters a and c will generate sequences. However, these are relatively basic solutions which are not very good in point of autocorrelation and long periods. And generally, a and c and m should be primes, and using that, there is a little risk of certain things repeating as fast as possible. However, this is of course the most basic solution, which gives us the natural numbers between 0 and m, and as we usually want the values between 0 and 1, we just need to divide them by m. The larger the m, the more distributed values of those samples would be. However, again, as I said, this is a very, very simple solution without which is not very good in computation. Currently, the most advanced and widely adapted pseudo-random generator algorithms is something called Mersenne-Twister, which we will not be elaborating on. This is implemented almost everywhere, including Python, and generally is to go for representation of random number generators. And we want that because if we have a number between 0 and 1 that is uniformly normally distributed, which was our requirements of pseudo-random generator, then we can use that number to get the probability distribution, at least of certain simple functions. And we do that using something called an inverse of cumulative distribution function, also called quantile function. As we seen before, empiric cumulative distribution function, the actual cumulative distribution function is a function that every number that assigns to every number x between the minimal value and x assigns the probability of events that the value of interest is in that interval. And that function easily maps from set x onto a 0-1 interval. That function actually is easy to show. It's an invertible function, at least in reasonable sense. And that inversion of this function, so the function that assigns x to a given probability, is called a quantile function, which is, as I said is an inverse of CDF. And if we have a quantile function, then it is relatively easy to generate a sequence. However, quantile functions are unfortunately defined only on scalar distributions. So if we have a distribution of one dimension, then we can easily generate with pseudo-random number generator a sequence of uniformly distributed numbers from P1 to Pn. Then we can compute the sequence of values of quantile function from that and we will get a sample from that distribution. Okay, so that's fun, but this is only for a very, very simple distribution. The distribution in one dimension. We can do different things. We can, for example, use a grid approximation. So represent our probability density function as some kind of probability mass function computed by values at grid using appropriate normalization. And we can sample from that grid as considering it as a discrete distribution, the probability mass function. Unfortunately, this comes from the old problems that we mentioned before with dimension light. So we will now see few examples of how sampling works depending on what kind of distribution we are using, and we will see how our statistics of interest behave during that sampling. Because we need to understand that when we are able to generate samples, we can get a lot of information about the considered distribution. So for example, let's take a normal distribution with mean of 1 and standard deviation of 1.25, so rather large standard deviation, and we'll generate 1,000 samples of them. As we can easily see, as we are adding additional samples, the uncertainty around the value of 1 reduces. It becomes a closer and closer representation of it here. Using histogram, we can see that, again, here's a histogram with uncertainty of each of intervals. We can see that this looks Gaussian-like, so we can see that the actual mean or expectation of that function is centered somewhere here with certain Gauss-like shape, which we should have because central limit theorem, and if we compare it with analytical result, our histogram looks analogical. What is important, however, when computing histograms is to assign the proper binning, because the wider the intervals, the more and more rectangular a histogram is. The tinier the intervals, the bins in the histogram, the more noise this representation has. So setting it somewhere in the middle is an important possibility to do so in order to make it reasonable. In case of ECDF, this problem does not exist because ECDF does not introduce you the concept of bins. So that's why ECDF is not necessarily the inverse of histogram, because that would be a step function. Here we just get a function that represents the entire distribution. Unfortunately, it's not as easily readable as histogram. In histogram, we generally can quickly see what values are most probable or not. In case of ECDF, this is not that simple, especially that ECDF is defined by the range of simulated samples. If we don't get large samples enough, then we will have a problem. Also, it can be rather sensitive if certain things can happen. In somewhere with outlier values, and sometimes it can be it can average things too much to be able to see a local phenomena. For example, if such peaks would be an actual property of distribution, probably they wouldn't be visible in ECDF. Second example. Let's take something that is not normal. Let's take a transformed normal distribution. So let's get samples from normal distribution and then let's put it through the inverse logistic function. So getting the values between 0 and 1. So sampling from that, we can see that our samples are constrained to the 0-1 interval, but the estimates here are kind of are still contracting to the one given value. And observing this shows us the concentration again around the expected value. And if we change the scale to the appropriate normalization, we can compare it with the actual analytical push forward of normal distribution function with the logistic function that we used. But these were normal distributions. Normal distributions are generally nice. They generate real numbers, but numbers far away from the mean are really, really improbable. This is not something that happens in more heavy-tailed distribution. Heavy-tailed distribution generally give possibility of events, of extreme events happening. And one of the most popular heavy-tailed distribution, or the distribution with heavier tails, is the student T probability density function, which is very similar to normal distribution, with exception that it introduces additional parameters called degrees of freedom, which is not necessarily understandable or fully applicable name, because it implies a discrete character. Something has a like a 5 degrees of freedom, but in case of computation it can be actually a positive real number. And student probability distribution, if degrees of freedom grow up to infinity, becomes a normal distribution function in the limit. However, if it's not fair enough, then we see certain changes. For example, we see that as long as we have a standard distribution, if degrees of freedom are larger than 1, then the expected value of it is 0, which actually is collocated with the maximum of the function. If, however, number of degrees of freedom is 1 or less, then the expected value of this function, the mean of this function, does not exist. What is the expectation of x given by this? So the classical mean, the first moment of that function, not any expectation that exists, just this one. In case of variance, we have a similar situation. It exists as long as number of degrees of freedom is greater than 2. If it's between 1 and 2, including 2, it's infinite. And if it's less than 1, the same like with mean, it's undefined. The special case of degrees of freedom equal to 1 is called the Cauchy distribution. And if we start to sample values from Cauchy distribution, we can easily see that even if we observe the situation, there is no real contraction around the zero value. Certain extreme events happen, and when we compute the averages, those averages can get shot in one way. Even if we increase the number of samples to 10,000, we will get the same situation here. The uncertainty will not disappear. There will be no convergence of the average of values to the some kind of mean function. And Monte Carlo computation is based on central limit theorem. And if everything is okay, then the estimator of quantity of interest, in our case the expectation of x time, expectation of x value, is it should be normal. So if we generate multiple samples and analyze the histogram of the actual estimator, we can see that this is not normal. And it's not normal because mean does not exist, so it cannot be estimated. It just looks like this. But that doesn't mean that those distributions are useless. Those distributions actually are very useful if we consider probabilities, for example, or other functions, as long as they exist. If we, for example, we are interested what is the probability of x belonging to the interval between -1 and 0, this can be very well be estimated, and probability is well behaved because we are only interested in the relation of how many samples are in the interval we want and how many are not. And this same goes for quantiles, medians, stuff like that. Those things are well defined and they have no problems. The moments, however, can be very, very wonky. And as we can see, also the errors are rather well behaved. The estimate of the indicator function probability, the probability of function between x being between -1 and 0 is around 25%, with a 1% of Monte Carlo standard error. And if we increase the degrees of freedom, we will get convergence to the actual value of mean. However, the uncertainty will still not be well represented. We'll be getting jumps in uncertainty coming from the jumps in the distribution values. And as we move again to the mean estimator, how it behaves, it's still not normal. As you can see, it's very flat here. It's better in detailed behavior, but the around the mean one is not really reasonable to analyze. Of course, that doesn't change the fact that including appropriate values will get what we want. However, if mean and variance are defined, then estimator behaves, of course, reasonably and converges with production of both uncertainty and the actual mean, and the estimator behaves very, very normally. And this will be everything for today. Thank you very much for listening to those two people that listened. Other people, well, I hope they will listen to it at the later date. So, thank you very much and have a nice weekend.